No, so English is not your native language, right? So there's a difference between can and may in English. So you can definitely lie down.
I have a roll from here, and just I should take advantage of it.
Do we have Mark on already?
Yes.
He's even there.
Yes.
Excellent.
So I'm not in.
You have that.
Yes.
Okay.
So let Dirk do it because he's sitting right there. Okay. Shall we get
We
started?
just have to hit the button later.
Who's going to do this chair slides?
He has to get in line first.
Yes. Okay. But you got an email for that.
Do you have the chair slides up? Yes.
But yes.
Great. It's fine. All right.
Okay, so there's only some stuff in the Icnrg.
That's from Sunday. So just start from where, just mark a line across so you can say it's Tuesday.
Sometimes things happen. Yes, but
Okay, I'll do text and I'll copy it back to
all right. Okay. Welcome. This is Icnrg. We are Börje Ullmann, Dave Oran, and I'm Dirk Kutscher. Quick reminder, the IETF IPR policy. Let us know if you see anything where you are aware of IPR in a timely manner. Next slide. Is the clicker working? Yes. Okay. So we have a mailing list, we have a web page, and our wiki. So on the wiki, we have an archive of all the previous meetings and all the materials. So if you couldn't make it on Sunday, for example, you will find all that stuff there. We already have a note taker, so thanks again, Maria. And you will find the notes on the Etherpad. If you are willing to help, feel free on the Etherpad. All the slides are on the tracker. Almost. Can you give the focus to the? No. Okay. So this is our agenda today. So I'm going to briefly give you the summary of Sunday's meeting. We have Greg talking about IP over CCN. Lisha talking about local trust management in NDN for IoT. Guillaume is talking about ICN in NFV environments, so leveraging NFV infrastructure. Cenk is giving us an update about the ICN for low power networks spec. And then we have Mark joining from California, giving us the updates on the CCNX specs. Ravi is talking about ICN in 5G. We have an update of the ICN for 4G. And finally, Lei Wang is talking about ICN and edge computing. Before I go on, is there any need to bash the agenda? Any changes? All right. So Mark is online. Perfect. Quick update of what has been going on. So Mark is going to talk about the CCNX documents in detail later. So they have been in the say IRSG review process, and that led to some comments that have been addressed. So more on that by Mark. There's also been an update on the FLIC draft. So FLIC is so file-like ICN collection, so manifest specification. Christian talked about this on Sunday. So check out the presentation and the other draft for that. No. Not so fast. Okay. Yeah, sorry for for keep spoiling the surprise. So, we recently believe we finished the disaster scenarios draft. So we did a last call on the mail list, and as far as we have seen, there were no requests for changes. So we think we kind of move this on towards publication after the meeting. We recently adopted a few drafts, so the terminology draft and also the deployments consideration draft. So these are now research group items. So that means we will continue spending time on them, and so that we are also, giving away change control. So if you want to participate in that work or have like critical comments or constructive comments, please check that out. We have other drafts that have been progressing. So for G, we are gonna hear later. There's also an update on applying ICN to IoT. See the main list for the latest update on that. So something is okay. There's a couple of new things that have been submitted. So thank you very much for doing that. So first of all, Luca and colleagues submitted a draft on MapMe, so managing anchorless mobility in CCN. There was a presentation on this on Sunday. So unfortunately, we did a little mistake with the name. So this is currently called draft IETF Icnrg MapMe. So it's not an adopted group item. So we kind of need to fix that, but we cannot really delete drafts easily. So that is something we will do later.
Just when you look at these drafts on the tracker, you can tell which ones are actually RG item drafts, even though this one's in the wrong grouping. It is in fact not marked as an RG draft.
Exactly. And there's an IPR declaration on the way for that, so watch out later for that. CCN info, that's a continuation of the Contrace work, if we remember that. So discovering information about the ICN network. Also on Sunday, check out the material. And the other one we are going to hear later about ICN for edge computing. Actually, ICN was represented at the hackathon on the weekend with two activities. So ICN Riot, maybe Shen can say a few words when he's doing his presentation later. And we also had a new activity that was started by Peter Maynard on the mailing list about ICN for SCADA network security, so like critical machine control. So we probably will follow up on this later. So Peter is currently working on that. I gave him some ideas, and we will discuss a few things. Okay, so this was the Sunday agenda. So you can see it was pretty full. So I'm not going through all of this right now. So one of the new things we did was a live demo. So Guillaume, who's also talking later today, demoed his ICN NFV approach.
And
now, next slide. So there is some hiccup with the clicker. I don't know what's wrong. Right. So quick overview of what the new things perhaps that you may have missed. So Paulo had a draft about ICN routing in opportunistic wireless networks, and Jungha was talking about architectural considerations for ICN with name resolution. CCN info I mentioned, and we also talked about key management for CCN NDM. And now it's time for the first presentation. And that should be Greg. So I hope this works for you.
Otherwise, you just tell me to switch the slides.
Okay.
If it doesn't work.
All right, so this is another new draft that I submitted. It was December. And I gave an overview of this work at the Icnrg interim meeting. I guess it was in the Seoul IETF meeting. That would have been a little over a year ago. So the title here, IP over CCN for seamless 5G mobility. The work at the time, when I did the earlier presentation on this, had not written up the protocol draft and had not done as much simulation work as we've done now. I've been working in coordination with a couple of PhD candidates at Colorado State University in the US, and they've implemented IPOC on the NDN Sim simulator platform, and so we've got some simulation results to share on that. Okay, so background here is, so ICN seems pretty attractive for mobile networking with elegant built-in support for consumer mobility via the stateful forwarding. Multipath connectivity is also pretty interesting, particularly thinking around 5G networking scenarios, as well as heterogeneous networks with Wi-Fi and 5G and LTE radios. The network caching and processing for edge computing, as well as efficient content distribution. But how do we get there, right? So network slicing is a key component of 5G for a lot of different potential applications. That's one way to potentially deploy ICN in a 5G network, would be to run it in parallel with IP. But effectively, that means for the network operator, you're running two networks in parallel, two networking protocols in parallel. You can run ICN over IP. That's a lot of the existing deployments of ICN are layered on top of IP and some on top of TCP. But then you lose the benefits of that are listed above, particularly the mobility benefits that are difficult to achieve over running off the top of IP. So we want to take a different approach and to explore the idea of using CCN as the forwarding plane for 5G. And I think we're not the first to observe that running natively ICN over a mobile network has some good advantages. And so if we start off with that as our forwarding plane, can we support all existing applications on top of that and effectively use CCN as a replacement for LTE EPC and get rid of all the tunneling and all of the control plane signaling that's required to handle handovers and all the inefficiencies that come with that. The idea is that if this becomes a compelling replacement for okay.
Sorry, that was my.
Okay. So then once you've got this as your forwarding plane and you're supporting all the legacy applications, now you've got the ability to roll out native applications and that take advantage of all the benefits that CCN or ICN provide. So here's how it looks in the network. So the user equipment supporting TCP and IP applications at the top of its stack have a shim layer we call IPOC, IP over CCN, CCN underneath that, and then on the radio link, it's running CCN actually through the E node B or G node B in the case of 5G, or Wi-Fi AP. It's natively forwarding CCN, and then we have at the edge of the mobile network a gateway device that interfaces with the rest of the IP world. The goals are supporting all existing applications, so there are no changes to all the smartphone apps that exist out there and servers, regardless of what protocol they use and how those protocols evolve over time. I say maybe not IP multicast. It's a little bit harder to fit into this architecture, but not impossible. But it's not necessarily a goal of this initial work. There are no change to IP stacks. Leverage consumer mobility aspects of CCN that work so well. support multipath connectivity, and do this all with high performance, low overhead, in order to provide this compelling replacement for EPC. So you think of kind of a simplified network architecture with a client and a gateway. Within the mobile network, it's all again, native porting, regardless of how many access points or radio links the client is able to connect to. They're all natively porting CCN and then bridging into an IP network via the gateway. So I mentioned on a previous slide, leveraging the consumer mobility aspects of CCN. So that's kind of a key piece of the approach we chose, and that the client is only sending interest messages. So all of its traffic towards the network is composed of interest, and then the gateway is only sending content objects in return.
Maybe it's easier you just tell me.
All right, so this shows essentially how the upstream packet flow looks like, the client and the gateway. An IP packet arrives at the client device. In this case, it'd be coming down a stack from the IP stack on top of IPOC. Each IP packet is encapsulated into a CCN interest using the interest payload functionality that exists in CCN. The source IP address goes into the name in the interest message, along with a sequence number. And that gets routed across the network to the gateway. Gateway de-encapsulates the payload, the IP packet. That goes into a packet resequencer. Not so important in the case of a single path connection, but in the case of multi-path connectivity, we want to deliver the packets in order. The name out of that interest goes into a new table called client interest table. It's a FIFO that just holds those interest names in order. The IP packets then are forwarded by the gateway into the IP network.
So that which I'm typical.
In the downstream direction, you see a IP packet arriving at the gateway. There's, in addition to this client interest table, there's also an ingress queue. Packets arrive into ingress queue and are matched up with a name that's pulled out of the head of that client interest table. This encapsulation actually is not just one-to-one. As many packets as can fit into the CCN payload, given the MTU of the network, can be packed into that content object. But it essentially consumes one interest name out of that client interest table to deliver the content object across the network back to the client. The client, again, we have a packet resequencer similar to what we saw on the upstream in the gateway. And so after de-encapsulation of IP packets, they go through the resequencer and then out to the stack in the device. Next slide.
Sorry.
Greg, before you get into the naming, are you going to talk at all about congestion control and how many of those interests need to be outstanding and how you avoid the equivalent of silly window syndrome in TCP?
Yeah, I give you a little bit of that. And if you have more questions, we can address it then. So naming convention is that we've chosen is to encode the IP address, the source IP address of the client in the name, along with this sequence number. And there may be other ways to do naming, but this is the format that we've chosen. Effectively implies that in the CCN network, that the gateway is advertising a route to prefixes, IP prefixes that it supports that map to where routes are directing traffic on the IP network. So I already mentioned the first part of that. The other prefixes or the prefix that the gateway would advertise into the CCN network is this initialization prefix. And that allows a client that's coming onto the network to discover the closest gateway and potentially periodically resend an interest to that init prefix in order to find out if it's a closer gateway than the one it's been using. And so that init prefix, when the client sends that interest, put a nonce in there, and gateway then responds with a message that includes all the IP addressing information that the client should use from that point forward, similar to what exists in TCP before TCP v6. This gets into now the interest content object exchange and make sure that there are enough interest names in flight and that client interest table is sufficient to support the downstream traffic. So to recall, when a packet arrives at the client, it can just send it. It just encapsulates it into an interest and sends it. The gateway is a little bit more complicated. It has to make sure that there is a name in this client interest table in order to be able to forward anything in the downstream direction towards the client. So we want to make sure that there is a steady flow of interest arriving that can support the downstream traffic. So in order to do that, we have two pieces to that. One is that the gateway has a target number of SIT entries that it wants to maintain during idle conditions. And the next slide I'll talk about how it manages that. And then on the client side, every time a content object arrives, it increments this counter called an IDC, interest deficit counter. Every time it sends an interest, it decrements that counter. And if it ever is sitting with an IDC that's greater than 0, then it will send an empty interest to the gateway in order to refresh the state in the gateway, effectively make sure that we have balance in terms of the number of messages that are flowing between the client and the gateway. And we bound that IDC so it doesn't grow in certain corner case situations, but we go on. The second piece of this is the gateway is in charge of increasing or decreasing the in-flight count. So a header field we defined in the ITOC header called the IDR, or interest deficit report, and it allows the gateway to effectively request for an increase in the number of interests that are in flight, or a decrease in that, or keep the same. So value 0 means effectively that content object contains the value 0 for the IDR. What that means is that the client is going to respond when it receives that content object effectively with an interest heading back towards the gateway. So that would keep the number of in-flight interests constant. If the gateway wants to increase the number of in-flight interests, it just puts a value 1 in the IDR. That effectively results in the client sending 2 interests in response to that content object being received. So then there are some very simple rules for managing or for this IDR. Effectively, if the SIT is full in the gateway when an interest arrives and it has no place to store this new interest, it will dequeue the name at the head of the client interest table and send an empty content object with IDR -1 to decrease the in-flight count. And if the number of SIT entries that ever falls below its minimum watermark, this min SIT value, then it's going to send the IDR value 1. Very straightforward. So situations where the in-flight count has to change. So one might be you're going from an idle state to a TCP file download. An initial window of packets arrives at the gateway, and it doesn't have enough SIT entries to handle the burst of packets. So it's a simulation of that situation. The main graph on the bottom, you can see in red is the plot of latency, and there's a short spike at the very beginning, which is enlarged in the zoom above. You see the nominal path delay across this IPOC network from the gateway to the client is 10 milliseconds. So you see a nominal value of 10 milliseconds for most of the traffic from the gateway to the client. And you can see the initial seeding packet achieves at 10 milliseconds of forwarding delay. And this, in this case, the initial window is set to 16, so we have a flow of packets. Some of them there are SID entries for, and they can go directly across the network to the client. Soon those SID entries get exhausted, and we've got some more packets that are sitting there waiting to go across the link. And they have to wait for a full round trip time for the SID entries to get refreshed. But then very quickly, the system kind of auto scales the number of interest in flight, interest names in flight, and fairly shortly thereafter, we get down to that nominal latency of 10 milliseconds again, until the TCP congestion window grows and it starts pushing more packets into the link than the link can support, and the traditional TCP buffer buildup happens, and so you see that ramping up at the end. But that's, I mean, aside from the, or not caused by IPOC, that's just the TCP behavior. Okay. One other aspect we deal with is PIT entry lifetimes. Expectation is that in intermediate routers between the client and the gateway, that PIT entries would have a finite lifetime, and if they were to expire in an intermediate node, then the name that's sitting in that client interest table in the gateway is effectively useless. It would not be able to carry a packet across the network to the client. And so we implement a SIT lifetime effectively as an interest name arrives, it goes into that client interest table, also is stored with an expiration time. And so when the one at the head of the queue times out, the gateway uses that name to send an empty content object back across the network to consume the PIT state. And then there's some rules for setting the IDR in that case as well, to effectively drain down the number of in-flight SID entries in that case, or number of in-flight interest names in that case. Yeah. So I'm not expecting you can read every word on that on the chart there. The intent here is to show the difference between a handover in LTE as it exists today versus what a handover could look like using IPOC and CCN. The intent is just to show complexity and simplicity rather than going message by message. But it's really a much simpler operation. There's no tunnel manipulation. There's no control plane messaging between MMEs and ENODs and SGWs and PGWs to set up and tear down tunnels and hairpin traffic through the old ENOD over to new ENOD, and all of that kind of goes away. Effectively, what happens when the UE attaches to a new attachment point in the network is, if it has PIT entries that's waiting for content objects for, it just resends those PIT entries on the new link. And in some cases, those PIT entries, those interest names effectively correspond to entries that are in the SIT at the gateway. And so when they're resent across the network, they just populate a forwarding state in the network, so that when those SIT entries are utilized at the gateway, the packets arrive, the content objects arrive at the client. In other cases, they may be interest names that have been used by the gateway and have already been sent across the network. If those content objects are cached in the network, then the UE is just pulling them from cache, some intermediate point in the network. Effectively, if the intermediate nodes in the network can support a FIFO cache or a circular buffer that's equivalent to a handover duration, then you have no packet loss during handover. Other things that are simple to support are soft handover. So adding a new network connection, a new radio link before you drop the old link. The UE can just start setting its new interests on the new link and wait for content objects to arrive on the old link, and then potentially tear that down once they've all arrived. And multipath connectivity is also pretty simple. striping interests across different links using whatever logic you choose to do for that purpose. And heterogeneous networks with different radio types, different network technologies, handovers, and multipath connectivity can be supported very easily. Just some simulation results with hard versus soft handovers. I'll go through that in something.
You didn't touch the Russian.
It's okay. So showing the hard handover in red and the soft handover in blue. From a throughput perspective, with the soft handover, you see a spike in throughput because for a short period of time, we effectively have 2 radio links. And so we're using both of those for a short period of time, and then and we discard the old link and only use a new one. From a delay perspective, you also see a drop in delay with the soft handover for an instant, and that is and that drop is not something that the end applications would necessarily see because this was actually measured at the input to the resequencer. Effectively, what's happening there is the new link doesn't have the TCP buffer buildup that the old link did, and so it's much lower latency connection for a short period of time. And so some packets in the TCP connection are arriving, in effect in this case, out of order, ahead of the packets that are waiting in a buffer in network on the other link. So we have 2 implementations, or 2/3 implementations. So one, a Linux implementation of both the client and the gateway, and we also ported the client side of that to Mac OS. Those were written on top of the Metis forwarder. That implementation was from a couple of years back. Then we have a more recent implementation on NDN SIM, which was allowing us to do some more sophisticated experiments, I guess, with different network scenarios and LT handover scenarios, etc. Neither one of those is posted anywhere public yet, but it's intended to be open source. So once we get it cleaned up in a format that's more easily shareable, we'll make it available to the community. That's all I have. So
Okay, great, thanks.
questions?
Any questions?
Thomas Schmidt, HW Hamburg. I have first maybe a more remark, and the second is a question. So for the remark, I mean, when I saw your intermingling of addressing and names, I was thinking of, I mean, when the people in Stanford in the trial project came up with the name-based routing, actually the main motivation was to eliminate the binding between node addresses and content names, and directly go on the name. So you eliminate DNS. Now you are putting IP addresses in the names, put an IP on top of it to inquire the DNS to get the names. So you actually you put 2 additional layers in it. Question is, I mean, can we do this simply? Can this be more, boiled down?
Well, so the intent is to support existing applications that are unaware of ICN. So all the both the client application and the server application
I understand
that
this,
are totally
but,
unaware. Right.
But still, I have no particular solution in mind. But I would question: can we do this simpler? And the second question would be related to this. What you mentioned in the aggregation effects, like multicast and blah blah, and the typical interest aggregation effects. Do they still work if you put end node addresses in the names?
So yeah, so you're right. That's why the caveat, maybe not IP multicast.
Well, I mean, I'm not talking about IP multicast, but about this multicast distribution system that for instance, arrives from interest aggregation. It's also a distribution system similar to multicast.
Right. So since we're only supporting unicast, IP unicast effectively, and it's the client source IP address that goes into the name. Oh, ostensibly only that client is going to be
Which makes
sending
it unique,
interest
yeah,
with,
yeah.
with that,
Yeah.
with those names. The case where interest aggregation does come to play is in the handover case where a interest name is resent in order to establish a boarding path. It only needs to go as far as the where the paths join, right? It doesn't need to go all the way back to the gateway. And so interest aggregation helps kind of just create the forwarding path to the new location of the network where the client device is.
Cedric Westfall, Huawei. I just want to, I mean, it seems that the comparison of the handovers is one is a soft handover and the other is a hard handover. I mean, it's kind of, one is simpler, but because one delivers different performance or result, I would assume.
So in terms of the complexity difference, so the one graphic showed just the algorithmic complexity, I guess, of the LTE handover.
Yeah, but that included buffering the packets, storing them in flight packets, and delivering those in flight packets, which you don't do in the IPOC handover.
Right, right. So IPOC handover is simple in both cases, but whether it's a hard handover or a soft handover, it's in both cases very simple. It's either just disconnecting one radio link and reconnecting to a new radio link, and then resending the interest from the PIT, or it's in the case of a hard handover or in a soft handover, just adding a new link and starting to use that for any future interest. Right, they're both very simple.
And the other comment I had was about so you put the on the IP side, it looks like the IP address of the source, but you still have to pin your route to the gateway, which it has to come. I mean, it has to come back to it.
Yes.
From the server. So I guess maybe you should put the. I mean, the IP address. You should rewrite the IP address so it goes back to that server or something like that, or to that gateway. I mean.
Yeah. So the idea is that gateway would be handling some subnet, right, or some set of subnets that the IP world can route to it, right? So the presumes that the IP routing topology is stable and not something that we're messing with, right?
Are you able to load balance over this type of stuff, or to parallelize different? Because you have to receive everything from that subnet and deambiguate at that point, and then maybe so.
So a network could support multiple gateways, each supporting a different subnet, and so you can scale that way, right? That any client is going to be interacting with a single gateway at any point in time for any IP address that it has. But a network could have dozens or hundreds of gateways if you need to for scaling.
Hi, Alan Chalik. I'll just follow on from that last point. First, if you have multiple gateways, that means that the client, would they each have different IP address ranges? So you would DHCP to each one individually?
Right.
So then your init would have to be farther down, so it was far enough down so that you knew which IP address the client should use, depending on which destination address it was going to. Another question I had was your PIT timeout issue. Have you done any computation to see how much additional radio traffic there is from the client needing to refresh those PIT entries continuously?
Not directly. It all depends on what the lifetime is, right? And I don't know that there's been much consensus in terms of what is a realistic lifetime for PIT entries in CCN networks. If it's on the order of seconds, then we're talking about a fairly low packet rate. I think in our experiments, we've been using something like 300 milliseconds as a timeout. And so if it's 10 packets every 300 milliseconds.
I'm thinking about, but some clients that appear on mobile devices even might have very long-lived TCP connections that they want to keep open, but are very low traffic. Idle command and SMT and IMAP, for example. There are various other things where you may have a very long-lived TCP connection, but very low traffic on it.
Okay.
If you end up sending 10 packets every 300 milliseconds to keep that thing alive. That might be the majority of the traffic over the video. One other question. I was just curious what you were doing about IP fragmentation, but that's just because I've suffered the pain of IP fragmentation too many times a month.
Well, we currently don't support IP fragmentation. I guess the assumption is that the MTU size of the ICOG network is sufficient for the de facto IP packet size. We don't have to support IP fragmentation, but we get more complicated, I guess.
Okay, all right. Thanks a lot, Greg.
Can I have the name of those?
Alan Sheiley, Cheiley.
All right, next, Lisha is going to help us to break out of the cloud. Yes.
She wants to present.
You're using yours, right?
PowerPoint has animations and
Last time, still made it work, right? That presented the thing.
You can use, yeah, sure, but you have to put it there, though.
Put it just here, and then you have
It's best if you let before you advance your slides.
I'd
So-
rather use mine. So sorry. Always come to it. So kind of about it.
you want to plug a clicker into your machine?
Sure. Yeah, great.
You can use this one.
no.
Okay.
Is it my turn? Introduction without-
It doesn't just hit, okay.
It's okay.
Okay. Then we can start from our beginning. Work.
There you go. Oh, sorry.
So the reliable system.
So something is not working today.
Okay, so here's the shot. I really I feel so grateful for the co-chairs having us the opportunity to present this paper. As you can see, this is actually published last year. And I think it's I agree with the chairs that I think maybe there's a value for people to hear this work. I especially thank the chairs because originally on this week we didn't plan to come here. We got so busy at home with so many other things. What other things? Among many things, two of the two activities that's open to everyone, and I hope some of you will consider participate in some of those activities. Especially this one, this is right before the ACM information-centric networking conference. So you can just hop on 1 hour flight to go Boston for that. After enough advertisement. So, when you write a paper, the first thing you have to consider is what is the motivation for that paper. For us, we were lucky because Amazon told us what's the motivation by creating events right at the time. As we stated here that as we try to finalize the paper, something big happens in Amazon, a huge failure. I don't know if everyone heard about that big failure or how big is big. So just for the fact of it, I want to use some Amazon's own words to describe the event in case you haven't heard about it. It's very interesting. So this thing happened it's just about a year ago, and exactly what happened is during some regular maintenance, someone made benign errors, and this error just removed larger set of servers than they have intended. And Murphy's Law always works. So because you removed some more servers than you intended, and what are those extra servers? Those extra servers support two other S3 systems. S3 is Amazon's replicated reliable storage. I think everyone heard about it. And those two other S3 subsystems, in turn, hold the index that manages the metadata and the locations information for all the S3 objects in the region. I don't have to say more. You can just from here understand the complexity of today's cloud services. And you think about this is the last failure, think again. So that's really get us to look into how we can develop local systems. By this, we do not mean to say forget the cloud. Cloud is tremendously useful. We will have it today, we will have it tomorrow, and into indefinite future. But the question is, can the local system work when this happens? If we all believe this will happen later, and we have to make the first question, give a yes answer. Look into why there's such a high dependency on the cloud. And we have to understand what a cloud-based IoT actually works. So we subtracted those functionalities out of those existing systems. I didn't do it, the student did it. So you can see why it's critical to have the cloud to be up for your home, like the cat feeding machine work. You can see that the identity management is in the cloud, the authentication is on the cloud, the device management, and the pops up brokers. And together with the storage and machine learning for data analytics. I think for the storage, for the machine learning stuff, they probably always will belong to the cloud, given that your home, maybe in the far future, will support those things. But cloud will be useful. But fundamentally is whether those other things, the trust management and the application semantics, whether they can be localized. So after many discussions and analysis, I should mention that lately, some of the functions has been kind of downloaded into the local servers. I think iCloud probably have your local, like your phone, can do some of the functions, but that's only after the initial configurations. Like for example, I don't think you can add a new device into your home without the internet connection. But after you have configured, have all the trust and everything, then you can have some basic functions managed locally. So some people asked us, why isn't that enough? Well, that is not enough. So, you know, the issues I think that people can understand. Clearly, you need remote services to achieve local functions that can hurt really the real-time performance. I'm going to give you an example that we used to exercise our design. And then you really subject local operations to remote failures. And I forgot to mention that the gigantic failure is only like marked the unavailability. I mean, only showed the unavailability problem. The bigger issues even, privacy. So I think it's just very recent that in the last couple of days, there is an exposure about the Facebook data being unknowingly utilized for other purposes. So think again about, you think your data will be kind of assured privacy for providers in the cloud. I think this was like that data leakage was not in the knowledge of the Facebook themselves. So we are actually in the NDN work, when we started in 2010, we immediately started looking into how we can utilize the NDN to enable local IoT systems. It's largely, I would give the credit to Professor Jeff Burke. He rarely came here. I think he showed up once, probably. But he's a leading person in developing the NDN applications. And because of his background, you know, he didn't do home IoT, but he's in the UCLA TFT, the Theater, Film, and Television School. So therefore, his expertise was in stage control. Before we had NDN, he questioned all of the people who do networking to say, how you people get so kind of get your head around it so many times when I want to do simple things for stage control to say the left side lights off and the right side lights on. And you have got me go through like many steps of gymnastic jumps. I need to get IP addresses. I have to figure out how to run up. You know, you have to understand he's not in computer science. You know. You have to have DNS servers and all of that. Why can't I just use my names to control the systems? And so therefore, when we started putting together the Indian team, Van Jacobson came to me to say, we must have this person. By that time, even though we were both at UCLA, I had not met him yet. Long story short, over the years, we decided we need to write things up about what we have learned to share with the community. So the work I'm presenting here actually split into 2 papers. The first one is published in the same conference, but the year before, to sketch out the basic model to say why NDN helps. Yesterday, when I gave a talk about using the blockchain technology for the IoT security, somebody asked me the question to say, what about the energy? Well, I forgot to mention that. Think about all the surveyor reduction. When you just have the NDN run directly on top of the physical transmission, that complexity, I tell you, saves tons of your energy as well. That removal of complexity saves your energy. So based on the idea to say that we can just name the data collected by sensors and build the security, not based on TLS, but based on the signature or otherwise the hash of the data generated by each producer, then you can build a pretty simple, but also very secure system. So if you are rethinking all of this cloud-based IoT system, I showed you that there's multiple dependencies on the cloud services, but exactly what are the essential services that you must support so that you can have a local autonomous home IoT system. I will save all the analysis and just show you the conclusion. We believe that given that we're going to name the data networking for the home IoT, so we will already name individual components and name the controllers. Then the functionality we need, just 2. One is the rendezvous, so all the devices find each other. All the different components of an application can find each other. And then the trust management. That is the essence of all the functionalities that the cloud actually provides. Because if you have that 2, all the other things can be built on top of this 2. So therefore, our focus mostly on how we can develop local trust management. The other day I was talking to Dirk and he said there's one thing that the secure sign-in. You buy a device from Home Depot. I think about this, your grandma buy the device from Home Depot. How could she just plug in the system in a secure way? But once you can achieve that, right, then you can get the other things. Also, we can do the rendezvous and we can have other things semi-automatically to get together to work. Now, so I guess this is mostly repeat what I have said in the previous slides. How we support the trust management and rendezvous is all based on naming. The fundamental difference, I believe, between what we have done, like compared to the work that has been going on, say in the IETF efforts, like the whole net activities, they have done lots of work, but it's, I feel, fundamentally different because of naming. HomeNet have this, I think the HomeNet as a TLD to say you can use that for discovery and other things, but that is not the name for your home. Your HomeNet called HomeNet, my HomeNet called HomeNet. When I bring my laptop to your HomeNet, my laptop cannot tell which HomeNet is real home and which HomeNet is not. Naming, okay, it's a unique naming for individual entities in the cyberspace. That is essential, the starting point for you to build this kind of local autonomous systems. So name things within the local context. It really requires each home has its own unique name. Uniqueness and global reachability are two separable issues. Let's not mix them together. But you need every home need a unique name, and from there you build your local context. If every home is called home night, there's no local context for your home. That's my first point. With that, then you can have the trust management. You can define in your home who has the right to turn on to adjust the temperature. Is it yourself or with your husband, right? That's an important decision in the family relations. You define the rules, assuming that, I think in many homes, the wife actually is a master. So that some the master, you define the rules. You use your key to sign to say this is a security policy in my home, Lisha's home. And then nobody will can alter it. And once you have those defined in a way that the devices can understand your definition, we have this thing called the trust schema. You use some kind of formal language to write down your trust policies, and device can really execute. That's how we can automate the home IoT system so that your grandma can indeed buy a device from Home Depot, plug it in, and plug it into a secure system. Now, the next question is really about the rendezvous. You buy a device, you plug it in, how would the other devices find it so that they can integrate the new device into a coherent system. Having said that, I would say, we already mentioned the other services applications can be bootstrapped with the three things. And also, I just repeat myself again, cloud services definitely it's important, will be there. It's just that we should not depend on that to run your own life. When the cloud service fails, you're still home, you can open your home door, right? rather than being locked out. Again, I like to inject all kinds of anecdotes. Being locked out has happened a number of times, and I have my third-hand experience. I have 3 students that did a wonderful startup called 1,000 Eyes in San Francisco. So they leased the commercial buildings, and one day they couldn't get into the office because some Amazon server failed. That's a real story they told me. I will say enough of that. So, after we define the basic concept, how do we know it actually works? We are doing science. We're called ourselves computer scientists. The only way you can prove your design actually works is through experimentation, real experimentation. So Jeff Burke had a student, that's the second author, Jahal. He actually developed this, I would say it's really demoware game thing about, they call the flow. I strongly objected to that as a flow has a totally different meaning in the IETF environment, and you can misleading people. Nevertheless, they like the word flow, so that's called flow. It's kind of an exploration game. You carry this gyroscope running around in your home, and so that there's the location sensors and knows where you are, and pretendly you can run into something, shoot something, whatever, and the game engine to show the display. So through this experimentation, we actually kind of empirically prove that the basic concept actually works. So these are the hardware they put together to make that whole thing work. I'm going to skip the details, talk about hardware. Let's talk about naming, because as like I mentioned, naming is the fundamental starting point for building the name the data networking or any applications on top of that. This is how the flow application exercise this naming design. You can see that there's the 3 parts of the naming. When you buy a device out of Home Depot, how you kind of inject the key into the device, and how would your home system accept the foreign components as its own. That the initial the trust bootstrapping started with something out of your manufacturer secret. You buy a device with a label, maybe with a barcode. If you can scan that in, that will be considered the shared secret between a device and your home system. And so there, you can install the shared secret with the device. After you integrate, so that's how you bootstrap the trust between the device and your system. And after that step, then you can see that in the flow implementation, we recognize the need. You still have two sub namespaces. One is in terms of devices, right? You want to manage the device, where it is, other things you want to do with the device. But then there's yet a different namespace. That's the application namespace. That's how you control, when you start playing games, where all the signals go, the request for data goes. That is in the application namespace, and you don't want to call it, oh, this is a sensor in my living room. And that will make the application development difficult. So a device simultaneously would have both a location, device-specific name, and also application assignment. The trust management, like I said, the home. Okay, good.
Yeah.
So it's very simple. Home has a master. The master decides who trusts whom and who sends which keys. You can have a hierarchy of keys, or otherwise kind of a multi-dotted mesh of keys, depending how define the rules. For rendezvous in the local environment, you just do a local broadcast. That's enough to find out each other. Again, the separate namespaces allow you to limit which devices receives which kind of a rendezvous signals to inform about each other. Now, given I run out of time, let's do a quick comparison between the existing IoT system based on the cloud and the NDN stuff. So you can see that for this, like I showed you earlier, all this trust, the application logic is in the cloud. And that makes losing the cloud will shut down your application. In the NDN, we fully utilize the cloud, where cloud is so great. It's just that when the cloud is gone, you can live on your own. That fundamentally requires you have this local trust. And the local trust, it really depends on your local naming. From the name, you can have a certificate. And from there, you build a local autonomy. You have lots here. And that's the signal. That's the exact information I want to tell you. I think that's also the difference between what we are doing, name the data, compared to we just think about how you transmit the bits. You have to establish the relations of trust of the individual components. This morning, I had a conversation with a colleague. He said, what's the difference between the word ICN and the name of the data networking? I don't want to make controversies, but I tell you, the fundamental of this new architecture is not about contents. So he asked a question to say, what's the conflict between the NDN and edge computing? Because isn't NDN so about the caches? I was a little shocked. No, NDN is name the data. It's all about the names. Okay, the content is merely the side effect. You can have the content stored anywhere because the content is named, signed. So it doesn't matter where it is, you get it, you can verify it. But all the trick of NDN is on the names. It's on the names. From names, you get the trust. And from there, you enable all the other things. Implementation, I'll skip it, the code. I don't guarantee all the code still work with the latest code development, as we are rapidly changing the NDN code base. But nothing. If something doesn't work, just let us know. Takeaway. So I'm done. don't know why this is done. Maybe I'm over time.
You're over time.
I have a button here to control it.
Why we depend so much on the cloud today? And I tell you, the market always pick the cheapest way to move forward. So we think that it's the so-called, all this cloud-centric implementation today, it's really just the market pick the least resistant path to reach the immediate result. From your home, from any device to reach cloud, that just matches this point-to-point delivery of the IP model so well. Look up the DNS, find the cloud service, get connected, and that's it. And also, there is a tremendous economical gain by the economy of scale. You put lots of servers out there, but it's cheaper than if everyone maintained themselves. More than that, the IT expertise is probably the most scarce resources, and not many people can run it. A cloud service is so great. But that gets us where we are, but we cannot stay here. Cloud dependency, we all recognize there's a number of problems. Some I listed here, and others I haven't. So this work is really tells you that, guys, there's better ways to build a home IoT systems, as I explained. And whoever interested in reading the paper, I put a pointer to the paper here.
Okay, great. Thanks. Good message. Please ask your questions after the session. We have to move on. Really, we have no time. So Guillaume is next with ICN over NFV. Sorry, there's no time for question.
HDMI. Thanks, Lisa.
Yeah, you can. But you have to stand in this box.
Okay. Good afternoon, everyone. My name is Guillaume Doyen. I'm an associate professor at Troyes University of Technology in France. I'm just waiting for the slides. I will present. Yes, this is what I see. Okay, I will present you our work towards the design and implementation of orchestration solution for the virtual deployment of information-centric networking. Okay, let's skip the outline. If we look back at ICN research, we have about 1 decade of research and development, and fundamental topics have been covered regarding architecture, packet specification, and so on. And now we are more moving toward advanced topics such as, for instance, security or traffic engineering. And we also have a set of operational implementation which are available. I mean, we have, for instance, NDNX, we have CCNX, and we also have some testbed open for research, such as the NDN testbed or Ophelia testbed. Whoops, sorry, I tried to, okay, it's very sensitive. So all these considerations make us think that we are now moving from design toward deployment phase for ICN. And when we talk about deployment, for sure, we cannot envisage a one-shot deployment of ICN, but we rather have to envisage some pragmatical solution, and especially a progressive migration given by or led by opportunities. These opportunities may be in terms of services that would best benefit from an ICN stack as compared to IP, and also topological location, for instance, in access, edge, or core networks that also best fit with ICN traffic engineering features. I mean, symmetric traffic routing and also caching. But there are also some other challenges to address, and I do identify 2 of them here. The first one is related to management and security. If we want telco to adopt this networking stack, we now have to provide efficient solution regarding the management. There have been a lot of efforts regarding the data plane and control plane for ICN, but it's also now time to design and implement a management plane for ICN. And the last point is the cohabitation with IP that must be handled, as we have seen in previous presentations. And this is a position of our research project, which is funded by the French National Research Agency. It started in 2014, and it will end this year at the end of September. And we have selected NDN as a core technology for all our design and deployments. So when we talk about deployments, the first question is where and how ICN stack can be deployed. And there are two different solutions, two classes of solutions. The first one consists in coupling ICN and IP. So we can mix protocol stacks. This is, for instance, the case of Cisco hybrid ICN we have seen last Sunday. Or we can leverage software-defined networking, and there is a set of references I provide at the end of the presentation. And beyond, we could also think about data plane programmability for ICN pipelines through, for instance, P4. And another type of solution consists in isolating ICN and IP. And if we want to isolate these two networking stacks, we have two solutions, which can be either the parallel combination with dual stacks nodes and hosts, or the serial combination with dedicated gateways. In the case of the Doctor project, we have been ambitious and we have tried to combine both of these solutions by leveraging network function virtualization. So the promise of NFV is that by leveraging the isolation property of virtualization, an ICN stack can be deployed independently from any other networking stack. We have a tenant domain and an infrastructure domain that are decoupled. And ICN is a tenant domain protocol stack, which is just offer a virtual layer 2 network. And at the infrastructure domain, we still have IP, which remains as a networking substrate carrying all the internet traffic. And that way we are able to either isolate the traffic, but also combine them to carry the traffic, whatever the destination is. We also have one other another advantage in NFV, which is the fact that NFV aims at reusing commodity servers and that way reducing capital expenditures, thus also being a facilitator for the adoption of ICN solutions. But this is a good part. We also have two major challenges to address. The first one is the design of efficient virtual network functions. And we especially here have a problem regarding the compatibility between ICN and NFV, since we have a stateful nature of the data plane for ICN, while we do really like to have stateless virtual network function in the case of NFV to allow dynamic operations, such as, for instance, spawning new VNFs, scaling up, migrations, and so on. And also, if we look at the management and orchestration, there is actually nothing to date regarding this part, since all solutions are related to pure IP VNFs. Okay, so you can see on this architecture our proposal. Perhaps if you know NFV, this architecture is familiar to you, since this is actually exactly the reference architecture provided by Etsy for NFV. We did not change anything regarding the role of components, but we just have adapted or redesigned them in order to take into account the specificities of ICN. So on the left part, we still have a virtualization layer, and we have chosen Docker as a core technology offering virtual computing, storage, and networking. On top of that, we have different virtual network functions. You can see here a router, NDN router, an ingress gateway, egress gateway, but we also have an NDN firewall and a signature verification module. And on top of these VNFs, we also have what is called Element Manager in NFV. Element Manager are local monitoring and management components in charge of dynamically pushing configuration rules into VNFs, for instance, FIB rules, and also monitoring these VNFs. And now if we look at the right part here, at the virtualized infrastructure manager layer, which is in charge of controlling all the network function virtualization infrastructure itself, Docker. Here, we have straightly reused Docker Swarm, since it offers the requirements we need. But we have designed novel components, especially an adapted VNF manager who is in charge of pushing the configuration and into VNFs, and generally speaking, managing the lifecycle of virtual network functions. And on top of that, an orchestrator that take as an input a Tosca specification. Tosca is a standard defined by the OASIS consortium, and Tosca is used in OpenStack Tacker implementation. And we have reused Tosca and adapted it to ICN specificities again. And this is input for our global orchestrator right here. Okay, now let's go deeper into the element manager. We have extended the work of the NDN management protocol, which already defines a set of metrics to monitor and provide a first step toward a full instrumentation of NFD. And we have extended it in order to fully feature the NFD data plane. So you can find here metrics related to faces, content store, and pending interest table. And there is especially here one metric, which is a bit size, that we monitor to evaluate the load of NDN router. For all of these metrics, we also have designed some micro detectors, one micro detector for one metric, who is in charge of solely detecting that a particular matrix is moving away from a normal behavior, and in that case, raising an alarm. To that aim, we model the distribution of expected behavior for one metric, and once the distribution moves away in terms of, for instance, mean value and also dispersion of data, then we raise an alarm. With this basic detector, the idea is to correlate events in order to be able to capture, for instance, security events such as interest reading attack or content poisoning attack. And to that aim, we have designed a correlation engine here, which is based on a Bayesian network, which relates together all these metrics through cause and effect relationship. And to do that, we have analyzed the two pipelines of NFD, the interest pipeline and the data pipeline to forward data back to the consumer. And we have identified the relation between these metrics, saying that, okay, when this particular event occurs, the set of metrics that will be impacted are as follows. And this has led to the design presented here. For the anomaly state represented there on top of the Bayesian network, actually there are two events we capture, which are IFA and CPA. Okay, now let's move to the orchestration part. As I said before, we have extended the Tosca format for ICN. If you look at the Tosca specification, you will see that there are 6 different definitions. Definition for virtual deployment units, virtual link, and connection point. For these 3 definitions, we did not change their definition in Tosca, but we have rather extended the notion of virtual network function in order to be able to deploy NDN router, gateways, or firewall. And we also have changed the definition of a forwarding path and graph. And for this definition, especially, we have removed all notion of layer 2 or layer 3 flow specification to rather consider prefix definition. And that way we are able to, by specification and by software configuration, to define all the routing purpose in the NDN network. Finally, a Tosca specification also provides some policies that are specify with event condition and action rules to apply dynamically. And we have especially considered 3 different policies that are the upscaling, signature verification, and dynamic firewall updates. Okay, regarding the orchestration component, we have a code written in Python plus REST APIs. We have implemented all of the components from scratch, apart from the Tosca parser, which has been reused from an existing implementation. We have 3 components. The NFV orchestration core is in charge of the initial deployment of an end-to-end service, but also enforcing the dynamic policies. And for the initial deployments, it sequentially deploys virtual networks, virtual units. It connects the virtual units to networks. And then there is a second engine, which is the NDN engine that takes parts of the second step, which consists in retrieving VDUs and network configuration and engage VNF configurations. And to that aim, actually, we have to take into account NDN forwarding paths extract from the Tosca specification, plus some information provided dynamically by the network forwarding network function virtualization infrastructure, information such as a set of IP address and endpoint identifier used in the underlay network. And by combining these two types of information, we are able to populate FIB entries into the virtual NDN network. Finally, we have the VNF manager who is in charge for the lifecycle management on the NDN VNFs. And it more or less acts as a relay between the VNF and the orchestrators in the sense that it receives the initial configuration and dynamic reconfiguration from the orchestrator, and it pushes them into the VNFs. And it also gets notification, I mean security alerts, I just show you with the Bayesian network from the VNF, and it sends them back to the orchestrator to enforce policies accordingly. Okay, so what are the current results we have regarding this design and implementation? We have considered a European telco topology, which is a clarinet topology represented right here. We have especially considered 6 points of presence, but the next example will only show 4 points of presence. We have selected this topology because the different links are available through the internet zoo topology dataset. And in each point of presence, we have instantiated NDN routers, a signature verification module, and the NDN firewall. For all this network, 1 point of presence actually is deployed into one OpenStack virtual machine. It means that under the virtual network you see here, we also have a second layer of virtualization. Okay, here is the service topology we have deployed. You can see the 4 points of presence with Berlin point of presence, Lisbon, London, and Amsterdam. You can see 2 peering routers on the left, on the right of the topology. And right after the first entry point after the peering router is a firewall that can be dynamically configured. And we have here router 4 and 5 here that are routers that can enforce dynamically a signature verification. And then we have the core of the network right here. We also have a good provider on the left that provide good content to consumers at the bottom, and also a bad provider who try to send corrupted content, I mean posoing content, to the legitimate users. And to help this provider to posoing the cache, we also have a bad provider, a bad consumer, sorry, here, that sends requests at a fixed rate to try to go faster than legitimate consumer in putting bad content into the cache. Okay, here is a snapshot of the Tosca specification we have implemented. So you can find on the left the specification for the VNF router 2 and for firewall 1, and on the right the specification of the 2 virtual deployment units, VDU2 and VDU4. Then you can find here the routing specification with the prefix here /com/Google. And you can see the definition of 1 forwarding path from router 2 to router X, from router X to router 4 to firewall 1, and then to peering point 1. And last, an extract of the policies that feature this topology. You can see here the Tosca definition for the signature verification enforcement if a CPA alert is raised by the element manager. And you can see that it targets router 4 and 5. And for both of these routers, when such an alert is raised by router 2, then for router 4, we will update the router mode dynamically to enable the signature verification. We have similar policies for the update of the firewall blacklist with prefixes that have been detected as corrupted. by the signature verification modules. And we also have a last policy which allow us to spawn dynamically some NDN routers to cope with the resource consumption due to the signature verification of router 4 and router 5. Okay, so now some results we have obtained on such a topology. The first result I display on the left here is the performance of our detection solution and especially our micro detectors. Do you remember I said there is one micro detector, one for each metric which is monitored in an NFD node. And actually we have leveraged the hypothesis testing theory to be able to analytically and theoretically anticipate the performance of our detector. And what you can see on the dotted curve here is the theoretical expectation of our detector in terms of false alarm probability according to the threshold we provide to our detector. And the main result here is that the set of lines is completely consistent with this theoretical line, meaning that for 3 metrics we monitor, here we have in blue the content store hits monitoring, the in-interest hits, incoming interest hits, and bit number size, we are able to accurately feature them through our micro detector. Here now, this is an extract of results for the Bayesian network classifier. And you can see here the dataset used to train this network. And you can see that starting from 250 samples, we start having an estimation of, I would say, abnormal behavior in terms of security that is very performant, since the percentage of error is about 2% right here.
Can you focus on the essential results because we are running a bit late?
Yeah, sure. I'm right on it.
Okay.
Finished for the monitoring part. Now the idea how to use it to mitigate the policy, to mitigate the content poisoning attack. I show you here 2 results. For a weak attack footprint, you can see here with blue lines the set of good data received by a good consumer, and in red lines the amount of data that is poisoned. And you can see that for weak attack footprints, our orchestration system requires more than 300 seconds to mitigate the attack. But when the attack footprint is stronger, I mean we have a rate of 128 interests per second, it takes less than 100 seconds to go back to the normal for the legitimate consumer. And if now we consider these 2 metrics, I mean the delay to mitigate the attack, but also the residual amount of bad data that are still go to the legitimate consumer, we have depicted here our ongoing work, and we make the attack rate evoluting from 8 up to 128 interests per second. And you can see that we have a good detection delay, since on average we are for strong attack footprint about 50 seconds, and for sure for weak attack footprint about 250 seconds. But we also have a large confidence interval here. That means that we need to do some more experiments to have something more accurate. And we get a very similar result, saying that here, if you look at the residual ratio of bad packets that still arrive to the consumer, we have here an amount of 2%, and here we have an amount of 9%. Okay, so this is the end of my talk about the way we could leverage NDN, and especially Mano component, for the deployment of NDN. We have currently a proof of concept for all the components of the architecture. Part of code availability is available here following this link. Since some components are still under publication and not fully implemented yet, they are still not available, but it will be the case in a few weeks or months. One open question, or just one motivation for my venue here, first to present to you the work we have done in this area, but The consortium is also open to serve Icnrg efforts and to push forward the deployment and standardization of this network paradigm. And what about pushing effort toward a standardized management plane for ICN? The track for future works we have consists first in evaluating our solution with real users. And since we have HTTP gateways, we are currently opening our testbed to students from Troyes University of Technology and Nancy University of Lorraine. We also want to go one step beyond regarding the content orchestration, saying that in idealistic perspective, we could have situation in which the Tosca specification would not specify from any sort the transport infrastructure, and we can decide that for content, the infrastructure should have to decide automatically if ICN is the best opportunity or if we could stay on a HTTP over IP solution. And the last point, which is an answer to the one of the two challenges I have highlighted, is the fact that actually we still face the stateful nature of ICN for NFV, and we especially have to consider the way we can cut or split NDN component into subcomponents in order to have stateless component that can freely migrate, be spawned, or scale up without the case, especially of the PIT component. Thank you very much.
Thank you very much. Looking forward to future results of this work. Please ask your question to Guillaume after the meeting. We are moving on. Next is Cenk with ICN LoPan.
Also, you're most welcome to use the mailing list for questions because it's quite underutilized. Take the opportunity. So I can pick up.
Yep. Thanks.
Yeah, these are not my slides.
No, your slides are coming in a second.
Nice.
You can start talking. Yeah.
Okay, so I will just start. So my name is Cenk from HRW Hamburg, and I will just revisit our draft that we have on the, as an adaptation layer for CCN and NDN on top of constrained networks. The first version for this draft, so we uploaded it in the Berlin interim meeting last year. Since then, we have 2 version bumps, and there's a third one coming. So just before I get technical, just a little recap on what actually happens here. So the main motivation for this draft was the following. 15.4 radios are actually widely used in the IoT. For example, the Philips Hue, probably everyone knows this, Philips Hue or IKEA Tradfino, and even the Amazon Echo Plus now uses 15.4 beneath, so they call it Zigbee. But the problem is that using 15.4, you have basically 2 main problems here, and these problems are in the protocol header. We don't have protocol identifiers, so actually, as a packet parser, you don't know what you have in the payload. Is it an IP packet? Is it an NDN packet, a CCN, or something else? The other problem is the small packet size. So on the physical layer, you can only transmit 170 byte in each packet. And this is especially for NDN and CCN a big problem because we have signatures in the data packets, which of course can get like 200 and more bytes. So what the IP world did is to define the 6LoWPAN. They call it a layer. It's called the 6LoWPAN layer. And this 6LoWPAN layer basically handles link fragmentation, and they have header compression built in and everything abstracted so that you can use IP over 15.4. And what we plan with this draft is to reuse these ideas for NDN and CCN so that we have ICN LoWPAN. So we just refactor out what was done in these 6LoWPAN groups and use it for ICN. That was the recap, and now to the updates. The NDN packet format had a version bump, so directly before we published this version, there was a version bump to TLV to packet specification version 0.3. So we did some restructuring of the dispatch fields and bit shifting and and reconsidered on how we compress the headers. We also did, we elaborate more on the name encoding for the IoT. So I will show this later, and also we did some number crunching and put some numbers in the draft in the appendix. So let's get technical now. This is actually how the NDN packet specification for an interest looks like now. So this is the newest version of NDN. And basically we just have the outermost TLV is an interest TLV, is just a message type telling now there's an interest, and then we have a length field and then the payload. And the payload is basically, again, you have a name which is, has the same structure. So you have a name TLV, and then you have the components of a series of name components. And at the end, you can have a digest. So, and then you have a bunch of optional parameters, which you can see here. So what we have now, if you look at the bottom there, you see like a dispatch octet. These are 8 bits that we use as a dispatch byte. So this is the same language as for 6LoWPAN. And this is basically, this one byte is basically sitting between the 15.4 header and the actual payload, so NDN or CCN. So we allocate 1 bit of this byte to just notify the packet parser. This is a compressed NDN or not a compressed NDN packet. And from there we go further, and we can basically just use 1 bit to encode the same as the interest packet, the interest type here. So we are getting rid of 1 byte and trading it for 1 bit. So we do the same with the name. I will talk about the name encoding after this slide, so I will just skip this now. And then there are some specialties. For example, in NDN, we have Boolean values, for example, can be prefixed and must be fresh. And in NDN, I mean, we use 2 bytes for this, which can basically, you can encode a Boolean value on 1 bit. This is what we're doing here. So we kill 4 bytes with 2 bits here. And then we just go on, we have the forwarding hint. We can use 1 bit for the type. And now I'm looking at the parameters here. So we get rid of the parameters type and just use 1 bit. And now I'm doing a little trick here. So if you can see this, the length field of the lifetime is actually variable. So the lifetime can be like 1, 2, 4, or 8 byte. What we do for the IoT is we are on a constraint network, and we limit this to 2 bytes. This means we can encode 65 seconds into this field. So we can say the lifetime in the pit is 65 seconds at max. And once we have the structure, you can see the nonce is limited to 4. This is given by DN. Now we have lifetime limited to 2 bytes, and now we have a hop limit limited to 1 byte. And here you can see the binary pattern. So it's a binary encoding. So we move the parameters up, and now from the perspective of a packet parser, you see the length field here. And if this length field is, let's assume 5, then the parser knows, okay, there must be a nonce and a hop limit because they both add up to 5. So this is a little trick we use here to implicitly remove the type field and the length field without using any bits here or the dispatch field. And after this, there's also a CID bit. I don't talk about this today. This is for the stateful compression. This is still future work. But basically, we would use, this is just a pointer to a further byte that contains state for the compression. So I promised to talk about the name encoding. Now we have 2 assumptions in the IoT. So at first, we say in the IoT, so we have this constraint environment, and we say each name component is limited to, here in this case, to 15 octets. So the name component length is like 15 bytes long. And we say that in this case, we say we use the uniform component type. So each component actually can be composed of different component types. And we say we just use the generic component for NDN names in this case. And when we have this, we can elide the type fields. So we move out the type fields. That's the second picture here in the middle. And after that, we can rearrange the length fields and reduce the length to 14 bits, to 4 bits, because I said we can at max have 15 bytes for a name component. And then we end up with the last picture in the bottom. So we see this is just we use just 1 byte to encode the length for the next 2 name components. And we use a stop symbol. And by using this, you can even get rid of the outermost name TLV length field, which is also 1 byte or more. I will show you the last picture in the bit level. It looks like this. So, because here's a trick now. So by using or by rearranging the length fields into 1 byte, we have an advantage with an odd number of name components, because now we can, here you can see the green pattern here. Now we can encode the stop symbol into the same byte that would use that would be used for the second name component. And by using this name encoding, we can see at the formula. I don't. So we win like a factor of 4 of bytes because of removing all the type fields and the length fields. And here's an example. So let's just assume we have a name, IETF 101 sensor attempt 2018. And in the upper part, in the upper picture, you can see an odd number of name components. And you see the outermost TL is here, the brownish color, and then the name series of name components, which contains the IETF 101 and so on. And after this name encoding, we get to a scheme where we have the length field used, or the length bytes is 1 byte used for 2 name components, and so on. And the last length field is again the mixture of the name component length and this stop symbol. That is why it's here green vertically. For even number of components, you can see that the stop symbol is using a full byte here. Where we decided for this actually to rearrange the bytes, because we keep the byte alignment, which which would make sense when decoding and encoding, because if you're byte aligned, you don't have to fiddle around with the names later when decoding. And here's an example how a real NDN interest would look like. So at the upper part, this is an unencoded interest. You can see the 1504 header is using, in this scenario, 9 bytes, and this is actually pretty reduced header size. We can also have header sizes by long header sizes, which are double the size by using long addresses, long MAC addresses. Here we are just using 2, so short address mode, just 2 byte per source and destination address. And then we have at the end 2 bytes for the frame check sequence. So you can see that the 1504 header is already taking up a lot of space of this 127 byte. And from here you can see that we have the outermost type length field that I said is the interest, and then the whole name, which is blue. The green we have here, the can be prefix Boolean value, let's say it here, and then there must be a fresh Boolean value, and then the nonce, interest lifetime, hop limit, and that's it. And from there, you can see the encoded interest below. So we throw away a lot of type fields, and we reduce the number of length fields. And in total, we save here like 22 bytes. But if you look at if you don't look at the 1504 header and just look at the payload below, then you can see that we go down by 40%. And if you also look at the type and length of the meta info, then we can see that we almost removed 80% of type and of meta information by using this encryption. Sorry, not encryption, compressing scheme. So let's look at the implementation, what we have currently. Well, as a write developer, I'm biased here, so I'm using write as the lower stack. For the 1504 access. And what we did is, or what we're currently doing is refactoring the 6-open. We have 6-open and write, but we this highly monolithic, and we try to pull out the refactor, the fragmentation and the dispatching framework, so that I can have easy access from the ICN world and use CCN Lite in this example here over a binary which is here called libicnl. I have the open source, the open source in GitHub here. It's basically just a static library that you can use for any kind of application. Yeah, and this is what we aim for. The next steps, we have, or some colleagues are working on Bluetooth Low Energy, bringing this into RIDE, and also the LoRa to elaborate more on these. And once we have this, I want to focus on, bring also ICN or NDN, CCN adaptations onto these layers, so onto these technologies for BLE and for LoRa. And after that, there are also other stateless compression schemes. Currently, we just looked at removing the type and length fields, which is pretty simple. But also you can do like here LAMP-ZIF encoding, or you can use Huffman encoding on top of this to reduce maybe more, to reduce the packet size more. And then, of course, where the most gain is in the safer compression. So we are also looking into this, and also we worked on this for the ICN RIDE hackathon at the weekend, so that we can assume a name prefix and just remove it, or elide the name prefix, and the IoT nodes are aware. So this is the same concept is done by the 6th Open, where they just remove an IP prefix and they assume it. And also there's we can leverage the PIT table, because we already have state that we have when we send an interest out and receive the data. So we can probably also cut apart from the name, the name in the data, because it's already stored in the PIT tables. This is also what we are looking into currently. And a couple of days ago, I got a pointer that Mark Moscow also had a talk about the header compression in Buenos Aires. So I tried to get in touch with him. I see him here in the Meet Echo. And we emailed, and let's see what happens there. Yeah, and that's the last slide. So any questions?
Great. Thank you. Thanks. Good work. Mark, how's it going? I see. It's kind of
How about now?
much better.
Okay, great. You have my slides up.
Yeah, I'm putting them up now.
1 second.
You should be seeing them now.
Yes. Okay, great. All right. Well, thank you very much for the time slot today. We got some feedback on the 06 drafts of the semantics and messages documents. So we made a few editorial changes to the drafts to address those. And this slide kind of summarizes the high level what happened. The security considerations, got a significant rewrite based on the feedback. There were also some nits about how to identify IRTF documents and some mandatory text that wasn't in there. So that's been added in. And then on the content side, there were some comments that the drafts didn't provide any background or motivation for what they're trying to address. So we added some new language around this, and then fixed a few technical style spelling and technical content questions. There wasn't any feedback on the messages draft, but we kind of applied the same feedback to that document. Next slide, please. So this table goes over the detailed changes. It says kind of what the changes are, but it doesn't say, the text of the changes. That's in the document, which is uploaded to the data tracker now. So in the semantics document, the abstract got some mandatory text about it being an Icnrg document, and the same for the messages draft. Then in the introduction, we cited a lot more work around the area. So the 7927 document from Icnrg as a context for ICN protocols. We cited the original Conex paper. We cited the CICN and CCN Lite implementations. We cited NDN as a related ICN protocol. There's about one paragraph that tries to nail down what the underlying differences between CCN and NDN, and which is basically discovery at the network layer. And we also cited the selectors draft as an example of doing an upper layer protocol for discovery in CCN 1.0. And a paragraph on that this draft is a consensus document from the research group, and we added four paragraphs with a high-level walkthrough about kind of how the protocol operates. In the messages document, we added just a quick background and cite the semantics document for everyone to look at. And we also cited the 7927 as context. We added a paragraph about the 2.2 TLV choice and the reason why we chose that TLV encoding. And we also cited work on header compression as a way to address the overhead for links that really need that. And then the mandatory paragraph on it being a consensus document. In the semantics document, we added a new section on architecture. So this describes what a typical network would look like, though it's not meant to be restrictive in that sense. And then in the protocol overview, we rewrote some paragraphs as per the comments back to us. And on the next slide.
Yep.
Okay. So it just takes my screen a little moment to refresh. So then the security section, as I mentioned, is a complete rewrite. So we added some text about these drafts are for a layer 3 protocol with authentication and not encryption. So just to kind of scope it. So because there were some questions about, well, what about encryption? And then we provide some usage guidelines for integrity checks and authentication codes and signatures, especially in interest where those could be an attack vector, a computational attack vector. We mentioned that we don't talk about how one arrives at keys or trust keys. We do cite the key exchange protocol as one way to exchange keys. And we discussed the key exchange and the encapsulating encryption drafts as examples of ways that you could create tunnels. And we mentioned that one could use other forms of encryption like broadcast encryption and proxy re-encryption for shared content. We discussed some of the security issues around TLV encodings of data packets, such as aliasing values, the need for schema value validation, and the potential issue of per hop latency due to TLV processing, which is, so most protocols, when they use TLV, it's in an end-to-end and not per hop. There's also an extended discussion of caching and cache poisoning and the motivation for the rules on cache behavior, which are in the body of the document. And we discuss our approach to hash agility and some of the limitations to that approach, and also mention that, you know, in CCNX, the name is a pure binary matching. So you don't have the flexibility that you have with like a DNS name of it being case insensitive. So there could be some issues for like phishing attacks if you don't have a good URI normalization or address it in like what a routing protocol will admit. And we also reference 7927 and 7945 for more background. The messages draft has the same exact language for security considerations. So please read these updated sections and get me feedback. And you know, if there's other citations that should be in there or other background that should be in there, please, you know, recommend it, and I'll put it in as appropriate. And you know, I'd appreciate any feedback if the NDN comparison paragraph is appropriate and sufficient. You know, I try to give what I saw as the core difference between the two protocols without really getting into the weeds of you know, too many details. And the same thing for security considerations. Please, you know, let me know if there's anything else that should be mentioned in here. Okay, next. So what I would like to do is either resubmit to IRSG or do an 08 draft. So, you know, if over the next 2 weeks you could get me feedback, and then, you know, in coordination with the chairs, we'll figure out, you know, either resubmit or, you know, bump it a revision as appropriate. And if you need more time to read the things, just let me know. You know, we can give you more time to read it, you know, to get the feedback. So that's the summary of what happened in the 07 draft. So this is probably the biggest change that's happened to the drafts in quite a while, you know, based on the IRSG feedback.
Okay, great. Yeah, thanks for taking care of finishing that work, and also for that very clear update presentation. Just looking into the room, is there any immediate question or comment? No. So thank you very much, Mark.
Okay, thank you.
Yeah. See you soon. Take care. I think you have to get out of the, yeah. Okay.
Just for the record, Robbie, 10 minutes. No. Okay.
So this is.
We'll give you rollover minutes, okay?
Any minutes you don't use now, you can use next time.
meeting.
Okay, okay, I understand. Okay. Okay, so this is an update to the summary of update to this draft. So where we are looking at the ICN, so basically the 3GPP's 5GC architecture, and see how ICN can be enabled in some native form in this architecture. So I will not go, because this the main difference, and I will just go through the draft updates here. So main draft updates is that we had Dirk, who has contributed his IP over ICN work into this draft to basically show that, okay, you can basically enable new kinds of the different types of ICN architectures into the 5G framework. So the one thing is that we changed this ICN. We had this ICN anchor point. We call it ICN gateway to avoid any misinterpretation. Basically saying there's no real anchor point from the ICN perspective. Discussion, yeah. So the main difference is that we added more details on how we could leverage the non-IP PDU provision for ICN in 5G. So it's more about the different considerations or challenges that needs to be addressed to ensure that to enable ICN to maximize ICN's efficiency within the 5G network. Again, we have discussion on this one on what I call with Dirk's contribution on IP on over ICN realization of 5GC, and there's been update to some of the use case scenarios. So here we have one use case. We had the use case considering a typical ICN kind of a CCN Indian kind of architecture, but we have an extension to also see how IP over ICN can basically do the same thing for smart mobility. And there was another contribution on multi-user VR use case. So this is again saying that you could fundamentally use some of the characteristics of the VR application to that could fundamentally benefit from an ICN deployment. So just to recap, the main draft objectives is to see how ICN enables to basically see how different features of ICN can be used to address a lot of the challenges of the 5G application. So probably people know this. You have eMBB, MMTS, and URLC. So there are a lot of challenging requirements there, and see how ICN Transmode can help that. So the first thing was to just because you have to look into the architecture and see how ICN fits in. So that main thing was to look into the architecture and basically see how ICN can be plugged in. And the main flexibility comes from the different principles that 5GC has followed in their architecture from the perspective of going from the perspective of network slicing or NFP kind of or NFV SDN principles that allows you to plug in new kind of control functions or user plane functions. So again, as I said, we have more discussion on non-IP PDU for native deployment of ICN 5G, and we end up with some use case scenarios. So this was the architecture that I had presented last time. So the main thing is that on the left side is basically the regular 5G architecture that's proposed today. We added some new control functions to fundamentally allow ICN UEs to connect to the network and fundamentally do some ICN session management to the ICN gateway so that you allow this ICN PDUs to flow between the ICN UE and to the ICN gateway. And there again, of course, since we don't want it simply not an overlay. So you could transport those ICN as basically IP-based PDUs, or you can do it in a native format too, right? So, so coming to this non-IP PDU considerations, so the main advantage here is that you can enable ICN UEs, whether they're smart devices or any kind of even IoT devices, without any IP configuration, right? So, and the maximum efficiency comes by enabling the ICN gateway in the RAN itself, right? So this allows you to fundamentally maximize efficiency, what you get from caching and mobility and so on within the 5G network. So we added a lot of considerations here in the sense like probably they're more about unanswered question of what are the different things that needs to be handled or to be addressed for this to work. So one is from the attached procedures and the control plane for the UE with non-IP PDU. So here you could, this probably you could use existing mechanisms to do it to fundamentally from the device authentication perspective. But again, with ICN, if an operator is actually running an ICN network, fundamentally it's not about transporting bits. He's actually providing you accessibility to certain services. So probably you have to go down a level lower to fundamentally even authorize users to basically authenticate services. And fundamentally, if you're doing services, then probably you're dealing with naming and basically other things like the trust mechanisms and so on and so forth. So there is, from the control plane management, there has been some work from the LTE to fundamentally handle this kind of scenarios, to handle non-IP PDU. You can leverage some of those features here too. From the user plane perspective, as I said, like if you're really bringing the ICN gateway towards the E node B, you don't have any more of that anchor point kind of architectures where you can do the centralized policing or charging or legal interception kind of things, which are fundamental requirements in these networks. So that has to be handled. And basically, how do you do when you're actually having a more distributed ICN network realized within 5G, within the 5G core, particularly saying that you're bringing all the ICN functions all the way till the E node B. Right. Pardon me? So ICN, again, the other thing with ICN is that you're carrying this kind of ICN in its native format. ICN itself doesn't include any consumer identity. So again, this probably you have to probably depend on some of the lower layers to handle it, or probably you could even extend the ICN layer to carry some of the consumer IDs, but fundamentally probably only till the 5G part of the network, but not beyond that. Then again, you have probably, there are probably these are all different ways you can identify the ICN PDU. So you have other identifiers, and if you read this draft, there are so many identifiers you can use in different contexts to do it. So the other one comes from the slice ID itself, exactly how do you take the ICN PDUs and give it to different ICN slices. So the other consideration is with respect to mobility handling. Again, it doesn't make any sense. Basically, you bring the non-IP PDU ICN in its native format to the E node B and then put it on a basic IP tunnel, rather than you probably want to handle everything without any kind of anchor points in the network. So, so as I said, it's efficient to co-locate the ICN gateway with the RAN, but again, with the RAN, you have again other control plane. If you want to handle mobility, you might need some ICN-based control plane support. So then you have to ensure that that control planes kind of integrate with the 5G's control plane to ensure the ICN mobility works. Routing considerations. So typically, today's 5G networks pretty much do kind of centralization management and routing, right? So again, when you're having this kind of flat ICN realization, then you run into scalability problems. So then you something like, to explore the feasibility of how distributed routing protocols can work in this scenario is something to consider. So I think here at somewhere, what I understand is that 3GPP is going in this phase with allowing more kind of mesh connectivity with some current like segment routing and stuff like that without GTP and stuff. So probably this would be another. So it's probably going to ICN. You could take some of those principles to see how those control planes are supported.
Okay, so this is how fast 10 minutes can pass.
Oh, sorry. I'm done, and I don't have much here. So the key thing is, again, mobile edge computing, you want to handle the service flows intelligently to take the ICN flows to the closest service points. So again, this architecture, as I said, yeah.
You have to move to the next slide now.
Yeah. So I'll go to the, yeah. Okay. Okay. So this is all based on how this IP or ICN can be done. Yeah. Okay. So the main thing here is that, to come to this point on next steps is how do you, so some of the things that we have outlined here is, is to, I think one of the benefits that I had a presentation during the interim was to see how ICN multicasting can benefit on the radio access. So something like we could investigate more or put more details around that into this draft, or again, non-IP PDU, as I said, there are more open questions there. Those can be further addressed. Separate. So again, the other thing is that how do you handle non-IP PDUs, particularly saying for IoT or smart devices? Those can be handled in a more detailed manner. Mobility handling over ICN in 5G. We have a seamless mobility kind of section discussing that. Managing QoS for heterogeneous applications. Again, if you're talking about flat ICN, then you have to think about QoS from the ICN perspective. And distributed policy charging and these mechanisms. So this is something that has to be handled the ICN perspective too as well. So anyway, so the main idea is that, the key thing is that this particular work could influence how how 5 or 3GPP could view ICN as mostly a potential kind of a network that can be enabled in the future releases, so considering that 5G is still 4-5 years out. And so that's a kind of objective we want to have kind of going further with this draft. So, so the main thing is that it would have good to have some kind of concrete feedback on if there is any particular set of problems that you see would be more beneficial. I mean, more from the people who are more active from the 3GP perspective, or also who is following this particular set of standards.
Okay, please provide your feedback on the mailing list. Really, no. I mean, it's 3 minutes over time, and so we have still 2 presentations coming. So next, what we're doing is we are taking Lei Wang first with the ICN for edge computing. Are you in the room? Yeah, great. Yeah. Mike.
Okay. Good afternoon. My name is Lei Wang, and I'm coming from China Mobile. Glad to be here and see you guys. Okay. Before the sun starts, first of all, I would say I agree or not the presentation from Professor Zhang, and in her presentation about the home IoT, I would like to call it edge computing devices in my presentation. And so I'm gonna give the presentation of the consideration on apply ICN to edge computing, and this presentation is related to the draft I submitted recently, and I put a link of this draft in the last page of the presentation. Okay. Okay. First of all, this is a new draft. This draft is not net technology, and of course, it has technology. So it gives the general architecture of the research on applying ICN technology to edge computing, and I also gave the reasons and opportunities of deploy ICN on edge computing, and I would like to give some technical consideration and relative scenarios.
The other way.
Okay. Okay. First of all, let's look at this board. Well, information-centric networking, I'm sure there are not experts here, so I'm not going to take long time to talk about it. Yeah, it's name-based routing, distributed local communication, information-based security, and multicast cache and forwarding system. So I would like to say ICN takes very important technological revolution and fundamental change in communication and networking. And when we look back, another side of the edge computing, it's close to users. Of course, it gives us no latency. It has data pre-processing, and it is decentralized system, local computing, storage, connectivity. And one of the interest and maybe the promising direction of it may be the intelligence on edge. So edge computing is also broadly divided on IoT and some other industrial verticals, such as smart city, smart grid. So when we just look at both, we may feel, okay, both technology, they have outstanding performance. And we have the feeling, maybe there's some correlative or similar properties of both, or maybe is there any chance we can use ICN to benefit edge computing? So, okay, opportunities of applying ICN to edge computing. First of all, ICN enable traffic convergence. Because in edge computing, there are a lot of devices deployed on edge, so it will cause a considerable uplink traffic on edge. And this kind of traffic also requires some flattening service. So we need the traffic is more convergent. And of course, the functionality complementary part with both edge computing and ICN, they have some relative or similar properties. But however, they also have some different properties can be complementary. Like we put night computing on edge, which means we give it intelligence. Maybe this can help ICN and give us win-win approach and benefit both, so we can get the maximum performance. And when we talk about ICN, there's one thing we always need to talk is its deployment. So is it worthy or is it realistic to deploy ICN on the whole network? Well, maybe we don't need to deploy it in whole network. Maybe we'll only need to deploy it on the edge, which can reduce the whole network deployer's cost and complexity and make the network more flexible. I'm gonna give some technology consideration apply ICN to edge computing, and this list is from my draft. I'm gonna take the next 2 pages to talk about it. Okay, first of all, the edge computing network disconnection solution. Well, normally, and it can happen, the network can be disconnected because of maybe energy failure, maybe some disaster. So in this kind of case, the data cannot be updated frequently, and it can cause some old data. I call it stale data here. And when this kind of data storage in the edge devices or edge nodes, it can also cause issue of storage limitation of the edge devices. And the edge computing traffic congestion, as we said before, there are a huge uplink flow traffic, and this kind of traffic can cause congestion. And the security part, yes, although it's edge devices, it is also connected with other devices or the cloud. Well, it has also need to face the risk from host attack. And just like the temperature control issues said in the previous presentation before, I think because the devices on edge are exposed to users, so we may need a very strong authority system. And well, does ICN or CCN really values edge devices? And the cost of the whole network ICN deployment maybe is too much. Okay, so start from first. In ICN network, edge computing devices or not does lead the data from the source node. It can be any node which get this data captured. And which means it doesn't need an end-to-end communication. So this kind of data can be updated into the edge node, and we don't need the old data. and we don't want the old data. And the caching algorithm, I think it's benefit from the data replacement policies of ICN, can help to replace the data and update the data efficiently and dynamically. And edge computing traffic congestion. This is a picture I got from my draft because time, I'm not going to talk about it. It's very simple. And the communication congestion is reduced by the traffic convergence. About the security consideration, well, because in ICN network, it's name-based security. So in this kind of case, when I don't need to worry about the host attacked. And because it's self-certified authority model, this can help or strengthen the authority model of edge devices or not. Well, does ICN or CSN values edge devices? Yes, of course. Naming on edge node gain more valuation, and the cost of the whole network ICN deployment? No, not necessary. Partial deployment of ICN on edge is enough to highlight the advantages. And of course, there are more consideration here. I'm gonna think about it and update it afterwards. Okay, now look at both. Okay, both perfect. So should we or can we combine them together to give us or give this two technology a promise future, and which can take more scenarios and use cases, and which need more consideration on technologies? Of course, we need to face more challenges. And reversed, I think edge computing can also benefit ICN. Like I said before, edge computing makes ICN more intelligent and more efficient. Okay, this is my email address, and this is a link of the draft. And we need more reviews and feedback, and the inputs and the contribution for draft. Really appreciate it and welcome. Okay, thank you guys are still here and listen to my presentation. I know it's quite late, so I give you this smile for you guys. About this cat, that's my cat. It has nothing to do with the ICN. I just love Catty.
Not yet.
Okay.
Yeah,
Okay,
thanks for
maybe one day it has something to do with ICN.
thanks for bringing this
Yeah.
work to us.
I'm a name it. Thank you very much.
Thanks. Is there any quick reaction from people doing edge computing today with ICN in research? Good. But you don't want to share it. Okay. On the mic, please.
One quick one would be, what is the definition of edge computing here? And also in the draft, what is the definition of ICN here? Because none of them are defined in the draft, so it's difficult to understand exactly what you mean with ICN and what you mean exactly with edge computing. So it's difficult to understand what problems, so what kind of ICN technology is bringing what kind of advantages to edge computing, because you don't know what you're talking about. I mean, it's not defined. I can't guess, because I know what edge compute might be. I can guess what ICN might be, but it's not defined. So,
Yeah, that's a good point. And I said it's not that technology. I may need some time to think about, and if you like or if you're interested, you can just join this draft.
There's much more to do there. What's that? I mean, just a simple example, like what, server on Wi-Fi, or it's 5G, or other applications, or
It can be wireless, it can be IoT, and it can be Wi-Fi.
that's the point. It would be helpful to understand and
Okay, I got your point. Because this draft is, as I said, is quite broad and general. I may next step, I may focus on some part of it, and make it more detailed, and then, yeah, I guess that's it.
What is the blue card?
No.
Okay. Okay. So yeah, thanks again. Let's get at least some more comments on the mailing list. I think there are some people who have some specific ideas how this can be evolved. We have a bit of time for the ICN over 4G draft update. If we can do this relatively quick. Thanks. This is the clicker, if you want it.
Hi, my name is Milan Stolic. I'm one of the co-authors on the draft for native deployment of ICN in 4G LTE mobile networks. So as an introduction, trying to gain some time here, as an introduction, the draft was about the holistic view of native ICN deployment specific to the 4G network. Some of its aspects would apply to 5G in the future, hopefully, but this is dealing really with the different scenarios of what happens if ICN is enabled or is not enabled in certain particular parts of the network. So we are looking at the options here. What if UE is dual capable? So if UE has dual stack and has the choice to make, and none of the other nodes in the network are ICN enabled. On another hand, what if ICN enabled through that and the UE is only IP capable? So the idea of the draft is to go through different scenarios and explain what it was doing. What needed to be changed with some specific proposals of the introduction of the transport convergence layer that will deal with this. So as a summary of draft updates, we want to thank the chairs and all the reviewers. We received quite a few comments, and we implemented these reviews in the latest change. Major changes I will show on the next slide. There's 3 of them, I believe. And as far as minor changes, in addition to Dirk, who was present from before, Ravi was listed as a co-author on the draft. And then also we have paraphrased some of the text and updated new references after some comments like that. For example, the QoS section has been clarified. We have identified that certain parity needed to be present between the IP and ICN. Now, will it be change in principle, or will it be, or not, is beyond the point. The thing is that the features such as prioritization, such as policing or shaping, in some shape or form would need to be present. Also, there were some minor changes in the security section. Security section has not really has listed the security concerns. Now we have that done. However, certain more research would need to be done. And I also seen in one of the previous presentations that Marx, I believe, would be dealing in details about security. As far as the major changes to the document, so we have added the reference. There was a comment that there is no distinction between live content like broadcast services and on-demand content. So we have added a reference to the broadcast and multicast technologies, eMBMS specifically, so that we would handle the multicast delivery in a pre-planned content. Live content versus that one that would be on demand in this example. Also, there were many references in the document prior to this revision to NDN. They were specific to NDN, and we were kind of going between NDN and CCN. So now we have moved from NDN to CCNX-based ICN protocol and messages, which is in line with the Icnrg drafts. Now, this we expect to be normalized once the whole harmonization effort has been completed. But this is on our side, we're not dealing more on the CCNX as opposed to mixing the two. And also, the change was that after one comment, we have removed the transport convergence layer, which, as a reminder, just is responsible for dealing with the specifics of choosing the right protocol depending on its presence in the next hop or in the transport. So, for example, if the UE is dual capable but transport is not, UE would need, this layer would make a decision which protocol to use and would pick the right protocol based on the presence on the next hop. So this has been removed from the protocol stack at P gateway, and the reason for that is in this case with dual stack ICN deployment in UE, we used to have transport convergence there, so the right thing would be to have transport convergence layer between UE and on the CDN side. In this specific case, P gateway is ICN aware, but we need to make a strict distinction between capability to do ICN transport and big ICN aware. Big ICN aware means that the UE should be able to attach via ICN even if ICN transport is not present as such, meaning that may not be capable of transport, but needs to be aware of the application level so that UE can be ICN attached, and then it can be sent over to the CDN side to where also the transport convergence layer would be present, and the transport selector would deploy the right conversion or the right choice, the right selection. As far as the next steps, we are currently implementing this in the lab. So the future draft versions will have updates based on the results from the lab trials, which we are in the process of setting up. Yes. Cisco systems. We will be using CCNX code, and that is being in the process of being set up. So the future revisions should have some results from the trials, from empiric results. And also, we need to now. This is not necessarily the next section or area for future draft updates. Could also be new experimental drafts. So these won't all necessarily be in this draft, but are certainly some questions that need to be answered in the future, such as investigate how to meet the IPQS requirements. Just like I mentioned, it has to be met some way in ICN. Then also investigate the impact of CUPS, the control and user plane separation and traffic offloading at the edge, so that we can optimize the user plane traffic path using ICN, which is the whole purpose of this, with UPF being closer to the edge. To investigate the realization of transport convergence layer, which we are introducing here as a concept, and our realization needs to be further investigated. Then impact analysis, ICN on mobility management, messages, structures, and flows. This goes from the fact that in this draft, we suggest that there will be no immediate significant benefit on control plane. This needs to be further investigated to see if there would be possibly in the future some benefit or further benefit from ICN in the control plane. The draft deals mostly with user plane messages. We want to investigate how ICN IP interworking gateway function will perform the conversion between ICN and IP primitives for data retrieval. In the draft, we are dealing with this at the end when the P gateway is ICN capable, but CDN is not. In that case, some level of interworking function would need to be introduced, and we need to investigate how would that work here. And then certain aspects, very important aspects of mobility networks need to also be examined, how they would react to ICN and how they would perform. I'm talking about lawful interception, billing, mediation, also network slicing and provisioning APIs requirements. So these are all concepts that would need to be investigated in this draft or in some other.
Thank you.
And thank you all for feedback, and please keep the comments coming. Thank you.
Thanks, Milan. It's good to see this progressing. I look forward to the experiments. Yes, actually. Okay, yeah. Please send your comments on our main list. So many things going on in ICN these days. It's really exciting to see. Do you want to bring up the final slides? Yeah. Okay. So just wrapping up this meeting. So it was a really busy week. So sorry we had to cut things short today, but we had really a lot of stuff today. Okay, so I hope you haven't made any plans for September yet, because there will be many cool events there. So there will be the RIDE Summit, September 13-14 in Amsterdam. So RIDE is the IoT open source operating system that is also working on CCN Lite, for example, and it's also has some so NDN and Riot. There are also developments there. So that is that. Lisha mentioned the NDN community meeting just 1 week later on the US East Coast. And we should mention, I forgot to mention the ICN conference that happens in Boston this year.
And we'll probably continue our tradition of scheduling an ICNRG meeting the day after the conference, because that's worked very well in the past. And the researchers who come to the conference who normally don't participate directly in this community have an opportunity to present their research and interact with the rest of the community. So while we don't have that nailed down, people should plan on that. It would be after the conference as opposed to before.
Mention also the dates for it.
So you do NDN meeting first, and then back to back we have the ICN conference.
But it's a weekend.
It's so it's 23rd. Wait a minute.
You didn't put the
Yeah.
But do you have it here?
the base.
Because the interim is on the 24th. So the ICN conference is
21 to 23.
Yeah.
Friday through Sunday this time. So please note that.
So it's a bit unusual timing, but it will be a cool event. So please book this in your calendars. So future ICNRG meetings. So considering the turnout this week, so I guess we will do a similar setup at Montreal. So a full day interim, and so a meeting like this during the week. Please send us your ideas and ideas for contributions, our topics for that. And so we mentioned the other meeting. So is there any other business?
If you have comments on the meetings and so on, please use the mailing list.
Thanks. Have a nice evening.
One of you take